All right, so we have one last section in kind of our conceptual chapter before we get into the actual analyzation of circuits. And we're going to quick talk conceptually about this concept of energy. And we've talked about conservation of energy, so we have kind of an idea of what our definition of energy is, and power. We've actually talked about that as well in the conservation of energy work and power unit. So if you recall, power, if you recall, was just your change in energy over time, or the work that you do over time, and that was our definition of power. So we're going to talk about how that pertains to electrical circuits in this section, and then we'll get into actually analyzing circuits in the next chapter. So energy and power. So when we're looking at a battery, we know that a battery has voltage or an EMF. But it not only does it supply potential difference, it makes a positive terminal and a negative terminal, but it's also supplying energy to the rest of the circuit. In this case, it's lighting a light bulb. So the battery is creating this charge escalator, which we talked about already, and it's transforming, I should say, chemical energy. So inside of a battery, we have chemical energy, and it's giving it electric potential energy for the charge. So the concept is we have these little positive charges. Let me change colors real quick. We have these little positive charges, and the battery acts as an escalator to get them to this plate. Then they're at the positive plate, so they have potential energy, like being at the top of the hill, and then they go from the positive plate across the circuit, across this light bulb, and then to the negative plate where it loses its potential energy. So kind of think about like changing from potential energy to kinetic or thermal energy. That's essentially what's happening, except the battery is changing chemical energy into electric potential energy. That energy then moves through the circuit, and it's dissipated across the light bulb, and that's being dissipated into thermal energy, which is keeping it warm and glowing because of the gases inside the light bulb. So this really does still satisfy this concept of the conservation of energy, except you eat food and run up a hill to get potential energy. You're doing work to run up a hill to get potential energy, and then you roll down the hill to get kinetic. Well, that's kind of what's happening here, except the battery has chemical energy to get electric potential energy, and then it goes through the circuit and gets thermal energy. So we can still analyze with these similar concepts some different ways of talking about electrical components. So first off, the rate at which energy is transferred. Well, before that was our explanation for power. Well, it still is. In this case, the battery is putting out some power or some type of power to the rest of it. And that's our change in electric potential energy over our time, or our charge times the voltage divided by the time. And more conveniently for us then, voltage or our charge over time, this concept right here is actually current. So the power of the battery source is the current times the voltage. And that is, again, it's still in joules per second or watts. Now, this is a really important concept, because when I look at if I have a battery, some of you might have some like rechargeable batteries that you use to have your phone, and those batteries are measured in a couple different things. They can be measured in watts, they can be measured in amp hours, and there are different ways of saying essentially how much power that battery has until it runs out. All right, so we got a little quick check here, and this one, it might be a little confusing at first, but we got a resistor that's connected to a 3-volt battery, and the power dissipated is 1 watt. So our initial case, I'll just give us a little I here, we know that P equals IV, and the voltage is 3 volts, and the power is 1 watt. But now it says the battery is traded for a 6-volt battery, so my new case, my final case, I have 6 volts, and I'm wondering what the power is going to be. And if I use this P equals IV, and if I were to just like solve for the current in my initial case and plug it in here, that wouldn't work, because the current changes as a factor of the voltage. So I'm actually going to use Ohm's law real quick, and instead of having I, because I know I changes, well, I is also V over R. So really, I got another equation. I'm going to talk about this in the next slide, that power is also V squared over R. So my other question is, all right, well, what's the resistance then? And if I go back to my initial case, I know that P equals IV, but if I want to get the resistance out of this, I could use this equation again, where power is V squared over R. So R is V squared over the power, which would be 9 squared over 1 watt. So I have a resistance of 9 ohms. And a resistance doesn't change, unlike the current that does. So now my new voltage is 6 volts, that's squared, over 9 ohms. I got 36 over 9, which is 4 watts. So again, that might have been a little confusing because we're not just looking at this basic P equals IV, but on the next slide I'll help you out a little bit with that. So here we have different ways of looking at the power. So before I had current times voltage, and the problem with our ranking task was if I change the voltage, the current's going to change as well. So I could also have, if I take V and I replace that V equals IR, now I can get I squared R. Or if I say, well, I is V over R, I can get V squared over R. So this is the power dissipated if you know the resistance, the current, the voltage. Any two out of those three, we have a formula for understanding the power dissipated. Now, this is important for things like light bulbs, right? So light bulbs, maybe you have a 60 watt or an 80 watt light bulb. Well, they all have the same voltage, right? Everything in your house runs on 120 volts. So if I want a 60 watt light bulb, I need some type of resistance value that gives me 60 watts, because this voltage is squared. So different light bulbs have different resistors in them in order to get different wattages. And then that wattage transpires directly into the brightness of that light bulb, assuming we're talking about regular incandescent. When we get into the concept, and I believe I've talked about this already, but the concept of LED light bulbs versus incandescent versus fluorescent, right? So they all have different ways that they work to provide some amount of light, but the wattage is going to be how much energy that it's dissipating in a given amount of time, which gives you that brightness. So that's really it for our introduction into energy and power. And then in our next chapter, now we're done with chapter 22, we're going into chapter 23, and we're actually going to learn how to analyze some very simple circuits and talk about resistor circuits and series and parallel circuits. And we'll be doing that in the next chapter.